Okay. Group I can't say this word correctly. Group homomorphisms. Homomorphisms. So show that the f of the following table is not a homomorphism from S3 to this group 1, 2, 3, the cyclic group 1, 2, 3, by finding b beta 1 and beta 2 in S3 such that f of beta 1 times beta 2 does not equal f of beta 1 times f of beta 2. So beta is given and f beta, you're given this table. So just have to find two values that contradict the beta 1 and beta 2. So, because that's how that governs, if that's the equivalency was true for all beta, then it would be a homomorphism, I believe. But it doesn't if this fails. So we let beta 1 equals 2, 3 and beta 2 equals 1, 3, those cyclic cycles. F of 2, 3 times 1, 3 equals f of 2, 3 times f of 1, 3. This should work out if it was a homomorphism. F of 1, 3, 2 we get from 2, 3 times 1, 3 is 1, 3, 2. F of 2, 3 is 1, 3, 2. F of 1, 3 is 1, 2, 3. That equals 1, the identity 1. And this equals 1, 3, 2. From the table, 1, 2, 3 is 1, 3, 2. 1, 3 is 1, 2, 3, so yep, it doesn't work. It's not equal. 1, 3, 2 does not equal the identity. So, therefore, it's not a homomorphism. Yeah. And another way I think you could at least predict which one would be is that if the orders are different, they should not work. In the end, I guess. Those would at least be a clue that probably wouldn't be working out that well. Like order of 2 and order 3, order 2, order 3, order 2, order 1. I think these three numbers, they probably are more likely to work out than these. But I'm not sure about that for this because it's explicitly wanting you to prove it this way. But okay, let R plus minus and R plus denote the multiplicative groups of the non-zero real numbers and the positive real numbers respectively. Let's say to be the mapping from R to R, basically R positive negative R to R plus, with zeta x equals absolute value of x. So the function is very simple, like we've done this before in the previous section. The absolute value function in the previous one. So explain why zeta is a group homomorphism. If x1, x2 is in R plus minus, show that zeta x1, x2 equals zeta x1 times zeta x2. That's what we're showing. We have to, this property holds, and it is like before, it is a homomorphism. So we know absolute value of x is equal to square root of x squared, and really quickly we can show zeta of x1 times x2 is equal to product of them in absolute value, and that's what the function gives you. But that's equal to square root of x1 times x2 squared, square root of x1 squared times x2 squared, and then you can separate the square roots and go back to absolute value form. So it's absolute value of x1 times absolute value of x2, and that's good because that's the format that zeta of x1 times zeta x2 is. It's absolute value of x1 times absolute value of x2, so they're equal to each other. And therefore zeta of x equals absolute value of x is a group homomorphism. Part 2 is what is the kernel of zeta. So zeta r plus minus goes to r plus, zeta x equals, just to restate it, absolute value of x. So identity of r plus dot, because we're doing what goes that part of it, equals 1. So kernel of zeta equals x is in r plus minus, such that zeta of x equals 1, otherwise known as absolute value of x equals 1. Because that's the identity. It's equal to the identity is where it's the kernel. So absolute value of x equals 1 implies that x equals negative 1 or x equals 1, so kernel of zeta equals negative 1, 1. Instead of negative 1, it includes negative 1 and 1. So part 3 is list the elements of the complete inverse image zeta negative 1 of 6. We did this before, but just inverse image negative x zeta inverse 5. So zeta x equals absolute value of x here. So zeta inverse of 6 equals negative 6 and 6. because negative 6 gives you 6, and 6 gives you 6 when you permanent a function. And the last one is let F be a homomorphism from the alternating group A4 to 1, 2, 3 a cyclic group. Use Pom 13 to show that F alpha equals 1 for each alpha in a subset of and also Pom 3 gives you A's in the kernel of theta, you know, as long as all this holds. But there's a lot of setup there, so let's do this another way. It also gives you, at least will show that it's that this applies. So F, so write this in nice in shorter words, the more brief. So F A4 goes to the cyclic group, which is the set 1, 2, 3, 1, 3, 2, and 1. Show F of alpha equals 1 for every alpha in that, like before. Just a little bit shorter writing. Translation of the Pom to a little bit more pure mathematical terms, if you will. So alpha is, yes, show that this is what you get. These are all. So one thing to note is that F alpha equals beta, we can write this as, which when beta equals, of course, that cyclic subgroup. An order of, so noting from this though, alpha is here. The order, so alpha includes these three things. It's one of these three all the time. The order of alpha equals 2. And beta can equal this. What alpha can equal is also these. In each of these cases, though, f of alpha will equal the identity. Yeah, the 1 identity. Cycle 1, which is equal to identity. So order of alpha equals 2 because all of them are order 2. It's 1, 2 times 3, 4, 1, 2, 1, 3 times 2, 4, 1, 4 times 1, 2, 3, all closed, you know. LCM of 2, basically, because this is order 2, this is order 2, so LCM of 2. 2 and 2. LCM of 2 and 2 for each of these will equal 2. Well, that's the order of them. So order alpha equals 2. If F is homomorphic, order of beta is divisible, divides order of alpha. And order of alpha equals 2 here, just note that. So order of beta equals 1. Oh yeah, so we have basically order beta has to divide 2 basically because of this. It has to divide order alpha, which is equal to 2. So order beta divides 2, that implies that order beta equals 1 or order beta equals 2. Beta equals order 1 is just identity. And order of 2 does not occur in set because 1, 2, 3, and 1, 3, 2 are equal to order 3. So beta is not equal to them for this case. So F of alpha, this all means that F of alpha equals 1 equals identity. For every alpha equals 1, 2, 3, 4, 1, 2, 2, 4, and 1, 4, 2, 3.